So let's finish up the substitution elimination mechanisms, and then we'll get into some of the So far, we've done SN2, SN1, and E2 mechanisms for our two general types of substitution reactions and our bimolecular version of our elimination reaction. So it only makes sense that we would have a E1 unimolecular elimination reaction that we have to contend with also. So we're going to talk about this a little bit, then we're going to talk about some of the nuances of these elimination mechanisms in terms of their stereoselectivities and Regio selectivity, and then we'll, particularly for cyclohexanes, substituted cyclohexanes are going to be one of the really fun topics that we get to deal with. And then a little bit of content on identifying, given a particular synthetic scenario, identifying which of these happen or if a combination of these things happen. So let's see. So for the E1, I'm going to do a substituted tertiary system, and just like the SN1, we're going to have a weak nucleophile / weak base, which is also the solvent. In this case, we're just going to use water, but we could use any polar product solvent, which is a weak base, weak nucleophile, so we could use methanol or ethanol here as well, just fine. And what's going to happen is we're going to get an elimination. Note that all three of these positions are equivalent, so all three of them have equal opportunity to be eliminated, but regardless of which one happens, you all get the same product. So I'm just going to draw this as our product of elimination, and you get a little bit of acid and a free bromide. Here's our product. So whether the hydrogen's pulled from here, or from here, or from here, because this is achiral, it's the same product, regardless of which position. So it's a good example to start with. Now mechanistically, this is similar to the SN1, where for this to happen, you have to have a slow step where you spontaneously lose the halogen, forming a carbocation. So a lot of the same constraints that were placed on the SN1 reaction are going to be placed on the E1 reaction. So let's see if we first step, bromine falls off. So what happens here is because the carbocation is relatively stabilized by the fact that it's on a tertiary carbon and the fact that we have this excellent leaving group which can host these electrons, we can take these electrons and move them to the bromine. And even though we can do this, it's not highly favorable. It's an equilibrium process. It's slow, and it doesn't favor the products. It favors the reactant side. But that's not going to matter, because after the next step, we're going to be consuming these products and driving it towards completion via Le Chatelier's principle. So what we have here What? Good. Okay, everything's still working. Let me redraw one of these arbitrarily. So I'm just going to, even though all three of these positions are equivalent, I'm just going to expand the bonds between the hydrogen and the carbon on one of the methyls. We'll just show the bromine as the bromide here. Let me get rid of the plus because it's confusing. It looks like there might be a charge on it. That's not a negative charge. And then what happens is we're going to have water come in as our base. So we've been doing a lot of discussion. In the last class, we talked about how nucleophiles like to donate their electrons to electrophiles, and bases like to donate their electrons to protons or acids, and that there's an enormous amount of overlap in here. But when something is attacking as a nucleophile, I'm going to try to keep it discrete. When something's behaving as a base and removing a proton, I'm going to try to keep it discrete. So in this case, this is going to act as a base. Go out and grab this proton that's going to be, as this bond forms, break this bond because we can't exceed the duet on that hydrogen, and those electrons are going to move over to be shared between the two carbons to satisfy the carbocation. And this is going to be a fast reaction and give us our product. So mechanistically, there's nothing wild going on here. It doesn't mean you shouldn't practice these mechanisms, because even though these mechanisms are particularly simple, you want to be really comfortable with the rationale for these mechanisms. So let's kind of address a question. When you see a methyl, you don't typically think of a proton on a methyl group as being acidic. Why is these 9 hydrogens acidic protons? What contributes to making these acidic enough where water can come in, can pull it off? And we kind of talked about the rationale for what happens in terms of the sequence of electrons flowing, but what allows this proton to let go?
Is it the carbocation?
Yes, it is. Because, so we have our alpha and we've got our beta, so this is a beta position to a carbocation. But what about the carbocation makes that proton acidic?
It withdraws electrons from the hydrogens.
Yeah. Yeah, and how does it do that?
Partial positive charge.
Right, so we can just think of this pulling electrons to it, but we also talked about, so what stabilizes a tertiary carbocation? Right, so we have these overlapping orbitals that give everything a way in which they can share charge. So because these are already hyperconjugated, we're able to pull some of that electrical density to satisfy that charge, and that's why it's more stabilized. But by pulling that electrical density, we've already weakened this bond, and this bond, and all 9 of these bonds. So the electrons have been going this way, so we're going to have a little bit more partial positive character on these protons already, which makes them easier to attack with these weak bases, like this water. So in terms of the rationale, you wouldn't normally think of this as being acidic enough to justify a weak base coming in and pulling it off. But in this particular case, we can because of the bonds being a little polarized from that hyperconjugation. So let's see. Any questions so far? Pretty straightforward. Okay. So, in terms of Regio selectivity for this reaction, what we just did was symmetric, so it didn't matter where it pulled it from. All 3 positions were equivalent, so no matter where it pulled it, it made the same product. We have something like this in water. We could have 2 different products. These are equivalent. So if we pull a hydrogen from here or from here, we're going to get the same product with a double bond here or a double bond here. If we pull hydrogen from here, it's going to be a different product. So we have the ability to make two different products here. And we have twice the opportunity from these positions. So what about this one? What if we pull this one? Okay, good. Just checking. Making sure everybody's awake. Yeah, you can't do it. It's a trick. Everyone's like, you have terrible tricks. Yeah, good. Just making sure you guys are awake. Some people are like, obviously have not had their Wheaties yet this morning, or their coffee in their Wheaties. I know. When you have to pull out the big guns, you just pour the coffee into the cereal, and then, yeah. What? I've never done this. I'm just that I'll admit. No, that's I'm not. Now, a Bud Light into a bowl of Wheaties, that's a whole different game changer right there. There we go, now we're waking up. Okay, cool. So, we've got two different possibilities. So, which one, just by assessing this, would you think is favored? I like it. This one. That's our major product. This is our minor product. So even though we have twice the opportunity to pull from these positions, this is a more stable product because we have more substitution around the double bond. Here, the double bond has a single proton. Here, the double bond has two protons. So you have more carbons around that double bond, which stabilizes it through that hyperconjugation. Now, you guys have noticed probably so far that all of our examples have been tertiary. Why do you guys think that makes sense?
She's only tertiary.
Right. You're not going to get spontaneous loss of an halogen from an alkyl halide if it's secondary or primary methyl. So what that means is that for E1 reactions to proceed, it has to be a tertiary alkyl halide. And in terms of relative reactivities, how do you think we would rank the relative reactivities of iodine versus bromide versus chloride versus fluoride? Most reactive or least reactive? All right, you guys are pros. Why?
It's the most stable leaving group.
Because it's going to be your best leaving group. Exactly. So this is going to be by far the best at taking those electrons spontaneously because there's room for them. Strong acids, strong acids, strong acids. If this was hydroiodic, hydrobromic, hydrochloric, not technically strong acids. So the base is going to be the stronger base, not as adept at grabbing those extra electrons. So a lot of the same things, same rationale that applied for our SN1s apply for our E1s here. So just like we had that that example where we compared SN1 and SN2, given sets of conditions, the same thing can be done for elimination reactions, if you're just looking at elimination reactions in a vacuum. Before I go on to that, any questions regarding this? So it is fair to say that this is, if you're asked to predict products, you'd probably want, and it said products, not major product, you'd want to draw this in as one of the feasible products. You would expect to see some of that being made as part of this reaction. Yeah?
What sort of ratio would you look at like this?
at least 90-10. You'd expect to see at least that much. I would be shocked to not see it if it popped up in a assessment of the reaction. As a pretty, like, you'd have to spend some energy to clean it up. So if you're doing an assessment of E2 versus E1, most of these are pretty straightforward. If it's primary or secondary, what does it have to be for the alkyl halide? Right. It has to be E2. If it is tertiary, it can be either E1 or E2. But there's some conditions you can take into consideration when we're looking at that. If you have something which has a high concentration of a strong base, then you'd expect to see it be an E2 mechanism of elimination. If you have no strong base, so you have these very weak bases like water or methanol or ethanol as the solvent, that would be when you'd expect to see the E1. So if you have a setup and you see something where you've got a tertiary system and methoxide is your base, you E2. If your solvent is methanol, E1 for your mechanism. And that's going to drive your prediction of products a little bit. Yeah?
If you had a fairly strong base, but not like super strong, would you expect to see both occurring?
We're going to get into that when we put all four of them together in a little bit. When we have a meth base, like conjugate, like a carboxylate, that's going to, versus a strong base, that's going to drive other factors too. So, because there's going to be competition between, in secondaries anyway. For tertiary, not as much of an issue. Let's see. So what's an example of a base that you're talking about? Like hydroxide or carboxylate or?
I wasn't thinking one in particular. But
okay. So if it is something that you look at and go, that's a base, this is probably where you're going. You don't typically look at methanol or water and think, oh, that's a base, right? Those are very weak bases, and they're very poor nucleophiles. But because we're attacking a carbocation, it works because it's such a strong electrophile. So if you have anything that you would typically look at and identify as a base, I would lean towards E2. Also, there's the solvent consideration. If you're in a polar protic solvent, it's going to quench anything like this. If you're, this is going to be the nucleophile and the solvent in these cases. So you should be considerate of your solvent effects also, and whether or not that base is going to behave as a good base. Good question. Other questions? Okay. So there's some stereoselectivity in addition to the Regio selectivity for this reaction for both E2 and E1. So for this reaction to proceed, what needs to happen is that the bonding orbitals need to be in plane with one another. So this is one variation of it. The other variation in which we have an alignment of orbitals looks like this. But this is not favored for a variety of reasons, which we'll get to in a second. Let me redraw this so it doesn't look ridiculous. Notice that, what's this conformation called as drawn?
Staggered.
This is staggered. This one is eclipsed. Which one's more stable? Staggered. Why is it more stable? Hyperconjugation. It's like the answer of the day, right? It's more, yeah, we have hyperconjugation. It's not because of steric issues in this particular way. I mean, there could be some steric issues if we had large bulky groups here, but just generically, we can say because of the hyperconjugation, where we have our bonding orbitals and our antibonding orbitals here, bonding orbitals, antibonding orbitals here, so we get that overlap between the bonding and antibonding on both sides, and we get like the equivalent of what you can think of as conceptually a very, very weak pi bond, which helps stabilize this conformation over that conformation where you don't have any alignment, so you can't have hyperconjugation in this particular structure. So this is more stable, therefore it's going to occur more often, therefore it will be available more to do an elimination reaction. So it occurs more often. Because we have this antibonding orbital here, when the electrons get pushed in here, it approximates a backside attack like in an SN2, which makes it easier. So it's kind of like what's that thing that a powerful executive would have on their desk where they pull up the ball and it taps the side and the other side moves? Everyone knows that, yeah. It's not just the pendulum, but it's the ball, so you have a bunch of metal balls lined up and they touch. And, okay, Newton balls? Okay. So it's like a Newton ball. These electrons come swinging in, it knocks that one out. Because of the alignment, right? So, yeah, that's everyone's going to use the Newton ball now.
That was just bad because it would come back.
Yeah.
Not if it hit it so hard that it broke the string. And if it was a reversible process, it could come back. So, yeah.
So it's more like a wrecking ball.
It's like a wrecking Newton ball. Yeah.
Miley Cyrus just
That's traumatic. Okay.
That's really good.
I fully expect the person who edits these videos to like simulate some kind of Miley Cyrus mechanism that comes in and like make sense of this whole thing after we're done. Get the views up a little bit. Probably get sued actually. Just don't put any music in it because they'll like YouTube will yank it immediately. Right? Let's see here. Let's see. Oh, the other reason this is favored is because there's no issues with the base accessing the proton. So if the base comes in as drawn, we're not going to do the proton first. Let's see here. Well, we could if it was an E2. We'll just start with E2. So as the base comes in, grabs this proton, pushes the electrons here, takes this off. As drawn, there's no problem here. If we put the base, but the base doesn't always approach from this side. It can come in from here, it can come in from here, it can come in from the other side. But there's no, other than these groups here, there's nothing blocking access. If a base is to try to do it here, it could access from this side, but the base would have a hard time being in this zone because of the electrical propulsion with the chlorine. So it removes one of the degrees of freedom the base can approach to do this reaction if you have this electron-rich group up here in proximity to the proton. So these are the three reasons for an E2 reaction, why we want to see not only the bonds aligned, but we want to see the bonds aligned so that they're on opposite or anti-sides in a staggered conformation. So let's see here. Now, if we have something like this, we have 2-chloropentane, 1, 2, 3, 4, yeah. We've got 2 hydrogens on the beta carbon. And because we have 2 hydrogens, we're going to have 2 different opportunities for one of the. So either we can do an elimination reaction, and it's going to favor Regio selectively being between these 2 versus over here, because this is going to give you a more substituted product. But we can align these so that either we lose this hydrogen and this chlorine, or this hydrogen and this chlorine. And that's going to give us 2 different products. So
Is it still E2?
this is still E2. So here we have the Z product, here we have the E product. Which of these 2 do you think would be preferred? E product. Why?
It's less steric.
Bulkier groups are okay.
Right, we got the bulkier groups further away from each other, right? So it's going to be both of those factors come into play. Having the bulkier groups trans from one another so that they have a little bit more room is going to make for a more stable product. So this is going to be preferred as a more stable product. So that's going to be our major product. This will be our minor product, but will still be a reasonably large enough product where it's not a 1% product. We're going to see 10% up of this being formed because both of these hydrogens are accessible. So when we talk about accessibility, let's take a look at a Fisher projection of this real fast with this bond. So if we've got okay, so this carbon up here that we're looking at with the chlorine is this carbon. So we're looking at it going from our 1, 2, 3. So we're going looking down between the 2 and 3 carbon straight on here. And so we've got a methyl group and we've got a hydrogen. So let's see where we want to put those. And then back here, we have an ethyl group and 2 hydrogens. So for this reaction to proceed, we have to have hydrogen in plane and staggered. So we can arbitrarily take one, put the other in here, H2, this makes more sense. So we've got this drawn up, these 2, that works. So if this reaction proceeds, we'll lose the chlorine, we'll lose this hydrogen to form the double bond, and which of these two will be formed?
It'll be the E.
Vote. Let's vote. We have a couple people saying E. We have a couple people saying E. One person changed their mind midstream, though. They started with Z. So let's go votes for Z. Nobody trusts me. I wonder why. Votes for E.
Eva.
Ziva. Yes. We have some tentative hands. These aren't like, ooh, call on me hands. These are like, sure. We'll go with the group hands.
Oh, wow.
But if you look at it,
Yeah.
one's on this side, one's on this side, that is going to be E. They're going to be trans one another across the double bond. So this will give you the E product. If we take this and put this hydrogen down here, bring this hydrogen up here, we can call this A, B, and we don't need to label the ethyl group, and just rotate the rear group and leave everything in the front the same. This can also proceed with the E2 elimination because everything's aligned exactly like we would expect it to be. But in this case, they're on the same side. So you're getting our Z product from that alignment.
Professor.
Yes.
Yeah, the stereochemistry of the chlorine would also.
In terms of which one's favored as a, well, it's not just the chlorine. So we've got, here we've got a chlorine that's fairly close to an ethyl group. Here we've got the chlorine equally close to the ethyl group. Here the methyl group is slightly close to the ethyl group. Here the methyl group is opposite the ethyl group. So this would have a slightly lower steric degree of interaction than this one. So it would be a slight factor in which one is favored and therefore more available. It also happens to agree with putting the bulky groups as far apart from each other as possible here as well. So having the bulky groups more separated here will help. Having the bulky groups separated here will help in the same way. So it's not a competing factor.
Is there any case where, isn't this,
Almost assuredly.
well, is there any case where it's whether or not it's R or S in the beginning will make a difference on products in the end or not really?
So we are losing any chiral center that we had when we
So
formed the
then-
double bond. So you can go from chiral to achiral, but it's not going to drive this
Okay.
necessarily.
Chillin'.
Okay.
Needed to review.
So that's if we have two protons that we can take. What if we have one? That narrows our range of possibilities. It means that you really actually only have one product that you can form.
So this would only have one proton.
Right. Or one proton that can be directly aligned but staggered from the leaving group. That is available. So we're going to start with an example with just one proton, but then when we get into cyclohexanes, there will be some scenarios because we don't have freedom of rotation where you can have two protons, but there can only be one product, which is why they're everybody's favorite, right? Everyone's super not enthused with that.
No, we're just
Scenario. Okay.
We'll get there.
I am too, but I'm faking it. Okay, so let's do. And we're going to throw a benzene ring in here because, sure, why not, right? Cool. Let's see, so we're going to get some generic base. So for this particular scenario, this bond has to be aligned with this bond and on opposite sides for this to proceed. So we can bounce those electrons down into a double bond, kick off our leaving group. Now, there's no other proton here. So there's only one possible way this reaction can take place. It's with this specific conformation. And because we can only use this specific conformation, there's only one way we can get a product. And if you're trying to draw this around a double bond, you're trying to pick which groups up and which groups down relative to each other. When this goes and this goes, this group's out, they're on the same side. This group's back, they're on the same side. So the benzene ring, hydrogen are on one side, and the methyl group and the methyl group are on the same side. So in this case, would this be E or Z as drawn? Okay, because this is our highest priority bulkiest group. Highest priority bulkiest group, not on Z same side, therefore E. Cool. Not Z same side.
You have a question.
Oh, geez, why do I have to keep getting the question? Yes. Go ahead.
Isn't there freedom of rotation?
Wake up, ask questions. Stop it. Just kidding.
I could just go.
No.
Isn't there freedom of rotation around that carbon-carbon bond? So why wouldn't it just revert back to so many different conformations?
This one?
Yes.
Yeah, all those conformations can happen.
Correct.
They're not all energetically favorable because it's a pretty bulky group, and you're going to be putting this close to some other relatively large groups. They're not huge. But yeah, this would cause all kinds of steric issues if you were going to eclipse conformations. But the important thing is, and so of all those possible conformations, the only one that can participate in an E2 elimination is when this bond is aligned with this bond. Because this is the only proton that can be attacked,
Okay.
and this is our leaving group.
Okay, gotcha. They have to be parallel.
So exactly, they have to be parallel and they have to be anti,
Cool.
so that we can get the reaction. Now, if we had two, we could have two different conformations that could result in products, which is why last example we had two different products. But because we only have one proton that can be attacked in this case, we only get the one product, so we have to be able to predict which one. That was a good question. Any other questions? I'm sure there are. Yes.
I guess I'm just still not quite getting why they have to be lined up to this to occur. Is that
So we had those three factors. You really need the equivalent of the backside attack. So as these electrons come in and add to this carbon so that you're forming a new bond while breaking a bond, you have to have a place to put those extra electrons. So you have 4 bonds to bonding orbitals that have electrons occupying it, and then you have these unoccupied anti-bonding orbitals that are higher energy, which align back behind the bonding orbital. So as these electrons come down, they have to have a place to go. And if we spin this around, there's no antibonding orbital aligned with this leaving these electrons coming down to facilitate that transfer to this nucleus. So there's that. There's the accessibility of the base, because if you put the bromine up here, but mostly it's having the antibonding orbital aligned with the bonding orbital, so that there's already a little bit of electrical sharing taking place by hyperconjugation. So it's a pretty easy step for it to come down into it while kicking this off. That's good. Let's see. Just historically, the stereochemistry of predicting the products what gets people on these questions. Most people are like, oh, it's elimination. I can pull a hydrogen off and a halogen off, add a double bond, and put it in the more substituted location. That's not typically what gets people. And if you do that, there's points there, unless it's multiple choice. You have to pick which way the major groups are going to be oriented based on whether or not this can be aligned with this. So just be cognizant whenever you're looking at this that you have to pay attention to the stereochemistry of the product.
Would it be reasonable to ask you to draw little representations of the orbitals and the path that the electrons follow in this standard confirmation?
For this? Okay. We need some more colors. Okay, so for this carbon, we've got an sp3 to s. For this carbon, we're also going to have sp3 to s. And then we're going to have these antibonding orbitals that are directly behind. And we're going to see one of the reasons this is stabilized because of its staggered conformation is we have that hyperconjugation taking place. We have this electrical density here, lack of electrical density here, and you get that sharing across this bond, and you get the sharing across this bond, and you get that for this and this one, and this one as well. So you have all this hyperconjugation taking place, which stabilizes this staggered conformation. So what's taking place here is because of this, we are able to have this base come in and take this proton, making the conjugate acid. When that happens, these electrons, as we form this bond, we have to be breaking this bond. So we have to do something with these electrons. So in some cases, you would see these electrons just be housed on this nucleus and have a free extra pair of electrons, negative charge. We've seen that in some mechanisms. But in this case, these electrons, because we have this great leaving group, can come down here. And what they're going to do is they're going to form that new pi bond. So what's going to happen is these electrons, as they come down, I show it drawing in this new bond, but as part of sharing between the nuclei, these electrons are going over here. As they form the new bond, as they form this new bond, we now have 1, 2, 3, 4, 5 bonds. So this bond's going to be the one that breaks because it has a great leaving group. And that's going to push those electrons to the bromine, which can house them as a decent leaving group. So, does that help? Okay. No problem. Let's see.
So would it be unreasonable, for a tester question to have you have given us this except it wasn't aligned, so then we would have had to just try to be like, oh well, it's either not going to react or being.
Oh yeah. So a really good question would be something like.
So then we just assume that it's in one of some sort at that point. H's are in.
Well, there's no stereochemistry drawn there. So you
Okay,
have
so are
to,
we not,
so you have to,
so do we not assume then that because the H's are like,
so you're like, okay, well, we have the bromine, it's going to be E2, one of the hydrogens has to go, there's only one of them here on this carbon. So I have to line this hydrogen so that it's aligned and anti, like this, and then you'd be able to predict benzene ring same side with proton, methyl group on same side with methyl group. So yeah, you're not necessarily given the stereochemistry.
okay.
Good question. Gamifying the questions. So simple mechanism, a little bit more involving. Like, man, I have to be sure that all of this stuff that we did in the first test was just gone. We didn't have to do it again.
So we're given that problem without stereochemistry.
Yeah.
Based on the only path for the mechanism to proceed, we
Mhm.
need to predict the stereochemistry of the final product.
Yes,
Okay.
for full points. If you gave me that, that may be right or not right, but if you got the product without stereochemistry, that's correct from the elimination reaction, there's points there. To get full points, you have to have the groups in the right alignment. Alright. Any other questions before we do cyclohexanes?
What do we have to do both R and S? Is that the, like, what do you have, if you just gave us that, or would you also specify R or S? Like for one of those carbons so that we can predict if it would be.
Yeah, I'd have to give you the stereochemistry. I'd have to give you the name.
Okay. Cool. Keep going.
Either that or you have to be like, well, since you didn't give me the stereochemistry, this is for RR, this is for SS, this is for RS, this is for SR. Here's your answers. Extra credit. I'd probably give somebody extra credit for that. I don't do it very often, but.
So you can just not give us that question.
It's a good question. Every time, the good thing is, when I'm in the middle of lecture and all these great questions come up, I'm like, oh man, that would be a great question for a test. I won't remember by the time I get back to my office. So, unless somebody comes and reminds me, which happens. People are like, did you put that on? Remember to put that on the test? I'm like, maybe. If it's like one of those really great questions. Questions have made it, but I don't tell on people when they do that. I don't like out them for bringing the really good question to my attention when I'm writing the test. Let's see. Sorry. Other questions before cyclohexanes? What's everyone's favorite part of cyclohexanes?
Looks like a chair.
Drawing them. We have chairs. What happened to chairs?
Flippy.
They get flipped. So ring flips, right? Like. So we're going to be doing ring flips again. Yay! Right? So remember, refresher on ring flips. Whoa. Somebody just said something over there. I hate ring flips.
I hate today.
Oh!
Better.
Oh! I hate everything about your chemistry today. Chemistry is terrible. Okay, so it's just the day. So we have the substituted cyclohexane. If we wanted to draw the ring flip of this corner comes up, this corner comes down. We're not going to change any of the relative orientations. There are people who, when I request a ring flip, will redraw the whole ring twisted and flipped and do all kinds of crazy stuff to it, which is very hard to grade, so I have to spend some time with it. It's usually not right because it was complex, unless they had a model. They're like, I'm going to mess with McGill. Spin it, flip it, spin it again like a Rubik's Cube, redraw it, and then I have to assess whether or not it was actually a ring flip. The best way to do a ring flip, leave everything the same way, move this corner up, this corner down. The group that's on top stays on top. The group on the bottom stays on the bottom. The group on top stays on top. The group on the bottom stays on the bottom. Don't ring flip by just inverting. That's the other thing people tend to do when they're resting on ring flips. They redraw this exactly like this chair, and they take B and swap A and Y and swap X, and that's not a ring flip. So also, when you're drawing, make sure that the axial groups are vertically aligned. They're up and down clearly. The equatorial groups are parallel to this bond is going to be parallel to this bond and this bond. This bond will be parallel to this bond and this bond. These are pretty good drawings on this one, but close, so that it's really clear what group is equatorial and which one's axial. It's not uncommon for people to not be sure, and they're like, "Yup." I actually saw a lot of that on the last exam. People like, and it's going randomly in the middle between the two positions for maybe partial credit. If it's ambiguous, I can't give you points for it. So make the bonds locations unambiguous. Also, when we do an elimination reaction and throw a double bond in this bad boy, we lose the chirality. You only have 3 groups, so instead of having an axial and equatorial position, that will go away, and the remaining group will split the difference between the two. So you have axial and equatorial, but then when we do our elimination reactions and throw a double bond in there, that third group is going to be splitting the difference visually. So that's going to be important to draw that into. You're not going to want to try to give that this location or this location, because that double bond's not going to want to support a tetrahedral structure anymore. It's going to want to support, not dropping things over and over, a trigonal planar structure with close to 120 degrees, even though the double bond's going to swing that a little bit. So get rid of that. There we go. So top stays on top, bottom stays on bottom. Top stays on top, bottom stays on bottom. Now, important thing with the ring flip, axial positions become equatorial, equatorial positions become axial. So this is equatorial, this is axial, this is axial, this is equatorial. X is now equatorial, Y is now axial, axial, equatorial. So that's our review of flipping rings. Now, how does this matter for elimination reactions? Can this cyclohexane with bromine undergo an E2 elimination? It's not an E2, that's redundant. It's an elimination. An E2 reaction.
Not in that confirmation.
Not as drawn in that conformation. Because when something is out equatorial, we don't have actual alignment of the bonds. They're still staggered from one another. So this group is staggered from this group is staggered from this group. So you don't have vertical alignment of the bonds in an anti-conformation. However, if we ring flip this, and it doesn't matter if it's the preferred product or not. This would be slightly preferred because the bromine will be out on the equator. Slightly preferred because there's no matrix steric interaction. So if we redraw this, whoa, that is not good. Top stays on top. Now the base can come in with all the bonds aligned and do the reaction. So in this particular case, this doesn't affect I redrew the double bond over on this side because it's the same thing regardless. So, so it's not confusing. Because the hydrogen came from here, so it'd be between these two carbons. But because this is just this, it doesn't matter where the bond is, it's the same product either way. Also, it could have come from this side just as easily. So now we have two protons that can participate in the reaction because the bromine is axial. So both the proton that's getting removed has to be axial and the leaving group has to be axial in whatever chair can participate in this E2 reaction. Now, in this example, it doesn't matter which one reacts, even though this is the one that does, because the product is going to be the same. It's just going to be a cyclohexene. So if this had participated, it would have given the exact same product. Now, that's not always going to be the case, though. So any questions about this before we move into... Yes.
Yeah, why? So you have the hydrogens and then the bromine and hydrogen on two, like column carbon 1 and 2 in the first one there.
So this one?
Yeah, 1. Label as 1. And then label the other one as, no, 2. And then over there, you've put the hydrogens on 1, on the place of 1. So that's why I'm getting confused, because it looks like
This one just comes down.
Right, so why?
This comes up.
Okay, so why isn't the number 1 carbon in the first drawing written
So it
up
comes,
in the
it
second drawing?
It
It
is.
looks like it's on.
It's just rotating.
I just did this. So when this happens, this one comes down, and this one comes up, and this one comes down, and this one comes up.
The one that your finger was just next to, that you don't have any. Yeah, 6. Where's 6 in the other drawing? Oh, okay.
Yeah, everything. So when this goes up and this goes down, the ones that are down, these two go up, and these two go down as part of the ring flipping.
So when you have a cyclohexane, the options for an attack are the hydrogens that are in a staggered conformation from
They have to be axial,
that have to be axial.
and they have to be staggered.
They have to be staggered. Okay. So if your leading group's not axial, you have to flip it.
Yes.
Make it axial.
That the leaving group has to be axial to do an E2 reaction.
And would that be fair game for us? Like, if given that first one where it's in the tutorial on an exam,
Mhm.
just to write, hey, we're gonna flip it, and it's gonna happen. Is that something that would be looking for an answer? Or would you just say, will not react as drawn, move on?
Depends on the question.
Okay.
So
Sorry,
this,
what you're looking for.
you'd probably get something that looks like this. And say, would this participate in a E2? What's the product? In this case, because there's no, because the product is going to be this, it doesn't matter which one did it. You could shortcut it, but there will be scenarios where you can't shortcut it.
Why did you erase the share confirmation of the product? You have the one you just drew, but you had one.
Oh, it's just to show that it's the same thing no matter what.
Oh.
It doesn't matter if it comes off of this 1 to 2 or the 1 to 6. It's the same thing. It's the same product either way. Because we don't have other substituents or functional groups around this that make them distinctive.
And if there were substituents, then you would want to
Then it would
share
matter.
confirmation?
Yeah. Then it would matter. So, I don't think we have quite enough time in the remaining 5 minutes to jump into elaborating on these. So we're going to pick this back up on Wednesday and get a little review on it and then jump into exceptions.